This video discusses how to graph quadratic functions that are in standard form. The quadratic function f of x equals a times the quantity x minus h squared plus k is in standard form. This is also called vertex form. The reason they call it vertex form is because the vertex is identifiable just by looking at the equation. The vertex is hk, and both of those pieces of information are available to us just by looking at the equation. I do want to point out that the x-coordinate of the vertex, the h, it's the opposite sign from the vertex to the equation, similar to what we've seen when we've studied circles. And the axis of symmetry, well, it's still the vertical line passing through the vertex, but since we know that the x-coordinate of the vertex is h, the axis of symmetry is the equation x equals h. We're going to graph quadratic functions in standard form by finding the vertex, the x and y intercepts, a symmetry point, and then we'll also state the domain and range in interval notation. Let's start with the vertex. There's no work to do when finding the vertex. All we have to do is look at the equation. Here's our h, and here's our k. We want the opposite sign for the x-coordinate from what we see in the equation. It's -1 in the equation, so it's going to be +1 in our vertex, but the k value, that's exactly how we see it. Our vertex is the ordered pair, 1, -4. Moving on to finding our x-intercept, we always let y be equal to 0 and then solve for x. You can solve this quadratic equation however you like. The easiest technique for solving a quadratic equation in this form would be the square root property. Let's isolate the part that's squared and then take the square root of both sides. Adding our 4 over, we get 4 equals x minus 1 quantity squared. Now we take the square root of both sides. Remember, when using the square root property, a plus or minus appears. So we're going to get plus or minus the square root of 4, which is 2. And then on the right, our square and square root cancel out, leaving us with x minus 1. I need to finish solving for x. Since the left side is an integer, and when I add 1 over, I'm going to need to combine those like terms. I always like to break it up at this point into 2 separate equations and then solve for x. That way I don't make a mistake. So we get x to be equal to 3 and x to be equal to -1. We have 2 x-intercepts, 3, 0, and -1, 0. To find the y-intercept, we always let x be equal to 0 and then solve for y. Y equals 0 minus 1 squared minus 4. There is no shortcut here. When finding the y-intercept for a quadratic function in general form, it's always 0, c, but that is not true when we are in standard form, so you actually have to perform the order of operations. We get our y value to be equal to -3, making our y-intercept the ordered pair 0, -3. Let's plot our points, find a symmetry point, and draw in our parabola. Our vertex is the point 1, -4. We have x-intercepts at 3, 0, and -1, 0, and a y-intercept of 0, -3. Using our axis of symmetry, which is the vertical line going right through the vertex, and our y-intercept, we'll find an additional point. Our y-intercept is 1 unit to the left of our axis of symmetry, Therefore, there has to be another point 1 unit to the right of our axis of symmetry. This will be our symmetry point. And it's the ordered pair 2, -3. Now we can draw in our parabola. We want to state the domain and range. The domain of any quadratic function is always -infinity to +infinity. The range for this example is going to be -4 included to +infinity. Let's look at another one. Notice that our leading coefficient this time is -3. That tells me that my parabola will be pointing down, and it will also be tall and narrow because of the 3. Starting with the vertex, there's no work to do here. All we need to do is look at the h and the k that are given in the equation. Remember that the x-coordinate is the opposite sign of what we see in our equation. We see +1 in the equation, so it's going to be -1 for our point, but the y value stays the same. Our vertex is the point -1, -2. To find our x-intercept, we let y be equal to 0 and solve for x. The easiest technique for solving a quadratic in this form is to use our square root property. So let's isolate the part that's squared. We'll add 2 over. And then divide by -3. -2/3 is equal to x plus 1 quantity squared. Now we're ready to take the square root of both sides. Remembering that when we apply square root property that a plus or minus shows up. So we'll have plus or minus the square root of -2/3 equals x plus 1. But let's take a look at this radical. We know we have to simplify the radical, but there's something different happening here than we've seen in the previous example. Notice that the number underneath of our radical is a negative number. This means that this will be an imaginary number. Imaginary numbers cannot be graphed on the Cartesian plane. Therefore, we have no x-intercepts. Moving on to our y-intercept. To find any y-intercept, we always let x be equal to 0 and solve for y. Perform our order of operations here. We get y to be equal to -5, making our y-intercept the ordered pair 0, -5. Let's plot our vertex, our y-intercept, find the symmetry point, and draw in our parabola. Our vertex is the point -1, -2. Notice where our vertex is, and also the observation we made at the very beginning. Since our leading coefficient is -3, we know that our parabola is pointing down. When you have a vertex that's below the x-axis and your parabola is pointing down, just doing a quick sketch here, we know that there couldn't possibly be an x-intercept. The algebra supports it, but just using our knowledge about parabolas, we could conclude that there would not be x-intercepts here. Y-intercept is the point 0, -5. We'll use our axis of symmetry, which is the vertical line going through the vertex, and our y-intercept to get a symmetry point. Our y-intercept is 1 unit to the right of our axis of symmetry. Therefore, we know there has to be a point 1 unit to the left of our axis of symmetry. And we draw in our parabola. Back to what we stated about the leading coefficient, it's pointing down. That's the negative. But since we had a number greater than 1, 3, notice that our parabola is quite narrow. The domain of any quadratic function is -infinity to +infinity. And the range in this case, -infinity to -2 included. Now that we're familiar with the standard form of a quadratic function, we can use this form of a quadratic function to help us write the equation of a parabola given the vertex and a point. So what we're going to do to write this equation is we start by plugging h, k, x, and y into our standard form. Remember that f of x is just the same as y. So when we plug in these numbers, the only variable that's going to be left is a. So we solve for a. Then we write the equation by plugging the a that we found and the given hk into our standard form. This is a similar technique to writing equations of a line using y equals mx plus b, where you plug in numbers, solve for b, and then rewrite the equation, but do not plug in numbers for x and y. Let's find the equation of the parabola whose vertex is -3, 5 and passes through the point 2, 0. So we've been given h, k, x, and y. We'll plug this into our standard form. So that'll be 0 equals a times the quantity 2 minus a -3 squared plus 5. Cleaning up what we have inside the parentheses, we get 0 equals a times 5 squared plus 5. So 0 equals 25a plus 5. Solving this linear equation, we'll move our 5 over. Divide by 25. We get that a is equal to -1/5. To write our equation, we're now going to plug that a that we just found and the given vertex into our standard form. We get the quadratic function f of x equals -1/5 times x. Remember, going from the vertex to the equation, the sign is always opposite. So this is going to be x plus 3 squared plus 5.